several and very distinguished awards, including the IEEE SPS award he will be receiving tomorrow at TOEIC. And another thing, so he's done the NSF Career Award, which is also very prestigious and vouches for his excellence in research, and a bunch of other awards too. So let's give a big round of applause to William.
Thank you so much, Alice, for the wonderful introduction. It is my great pleasure to visit KAIST. My third time in Korea, first time in Daejeon. And again, thank you for coming. And today we're going to talk about compositional and collaborative generative AI designs, which I think could be the next big thing for AI. Okay, first thing is that, I think we in the academia, in computer science, in AI, is at a very unprecedented time because we really need to figure out, right? So what we need to work on. Whereas if you look at the industry, they're just like every single week, right? There's a new language model that was released by the industry. And you can see that a lot of these companies, they're focusing on scaling, right? To build like bigger models or trying to deploy, right? All these different, language models and generative AI systems into their product to make money. In the industry, that's what they're focusing on. But in the academia, I believe we need to do something different, right? Mm-hmm. On this side? Okay. Okay. Mm-hmm. Well, where's the camera? Oh, that's the camera. Okay. Let me see if I can. Uh-huh. Mm-hmm. I just realized that's the camera actually. Mm-hmm. Mm-hmm. Oh. Oh, interesting. That's human-centric AI. Uh-huh. Uh-huh. Mm-hmm.
Okay, now, okay, now you're in.
Mm-hmm.
I think it's fine.
Okay, great. Okay, perfect. Let me continue. So then the question is AI in the academia, right? What do we do? I think we need to invest in long-term research problems, right? That this industry, these companies, they cannot afford to, because industry, they're driven by the earnings, right? The quarterly reports, they have to make money. So that's why they cannot afford, right, to invest, right, many of the long-term important research problems that are potentially adventurous, but we can actually do that, right, in the academia. So what are some examples, right? So I've been thinking, what are some problems we can work on, but can actually make a difference? Today's talk, I want to address 3 fundamental challenges in language model and generative AI design. Specifically, I want to talk about theory, right? So for example, how do we understand the science of large language models? Is it possible, right, for us to look at some theoretical insights, right, for the language model so that can help us to build better language models in the future? The second part of the talk, I'll talk about reasoning, which is, how do you use, right, language model to solve complicated problems that requires reasoning? And how do we reduce hallucinations, right, from these language models and solve more challenging problems? And third, I want to talk about, the intersection of vision and language. How would you be able to fix, right, these compositional errors for generative AI systems and improve, right, these vision language systems? Because used to be the case that vision and NLP are so separated. Right now, vision language, they're getting closer, right, closer in many applications we've seen. All right, so let's dive into that. The first work we'll introduce is called language models or latent variable models. This is a joint work with many of my students, Xingyi and Wang, Michael. These are my PhD students. Mark Stivers is a professor at UC Irvine, and this was presented a few months ago at NeurIPS last year. Okay, so I assume that people are already familiar with this emerging abilities of large language models. And if you look at, Wei et al. Paper from 2022, while there are these different tasks, right, that language model exhibit some of these emergent behaviors. If you look closer, the first task is called modified arithmetic. So what that means is that you're not teaching the language models to learn this arithmetic or these operations, for example, addition or multiplication. You are redefining the meaning of these operators. For example, 200 plus 1 is no longer 201. Now you say it's 202, right? So addition plus 1, that's the new definition for this operator. So if you give such a new definition, how long, right, this language model can learn this new meaning for doing this new operation. Turned out that you need certain skill, right, in terms of training, then language model can actually do the task really well. So that's quite interesting, I think, for the community with regarding to the size. What we want to talk about is one particular type of emergent behavior that is called in-context learning. That is a relatively new paradigm that emerges in NLP in the last 2 years that we look at, how can we have a better understanding of in-context learning and how we can improve in-context learning. Okay, so this particular paradigm shift, it is happening in NLP, but it's also across NLP in computer vision and in machine learning as well, that before 2018, we used to think about machine learning as just, okay, I take some data, I train a model, and I test, right, on this existing model. But then in 2018 in NLP, people realized that what if I actually collect, right, the entire Wikipedia, and then I train a model, so this model now knows the basics, right, about English, about Korean, about different languages. Then having some new tasks, I don't have to train a model from scratch. I can just fine tune this, basic English model or basic Korean model with my in-domain data, then it can actually do it much better, right, for many different tasks involving language. But again, paradigm has changed in 2022 with the introduction of InstructGPT and GPT-3 that people realize that, okay, I don't even have to do fine tuning. Maybe for some tasks, I can just use prompts, right? I can write particular prompts. For example, this is English to French translation. I can select some examples. Okay, sea otter example. Peppermint means French, and then there's another word, and then French translation. Now I give this query cheese, right, and then I ask language model translate cheese into French. Okay, so this is what we call in-context learning. That the model is learning what task it's trying to solve within the context during inference time. The parameters, right, of this language model was frozen, right? So we don't actually change the parameter. Okay, so that's in-context learning, but the question is, how do we understand, right, in-context learning? It worked really well, but what do we know about in-context learning? So in-context learning, there are a couple of things. So one thing is the demonstration. How do you select, right, this English-French translation pairs? How do you select it such that you get better performance, right? And of course, how is that related to your test examples? What are the things you should choose? There were some studies in 2022 on the space. People were looking at similarity using retrieval-based approaches. Can you select, right, demonstrations that is closer to a test sample? Sometime, right, it worked out really well, because imagine you're translating a word between English and French, and you're choosing the most similar example pairs from your data that is most similar to your test query. Some cases, right, it work out really well. But you can also imagine that if you need to do out-of-domain generalization, there are no similar example in the training time, it might not work very well, right? So there are certainly these advantages of doing the similarity retrieval-based approach, but in some cases, if there's the out-of-domain sample, it may not work out very well. From the explanation point of view, there's also people who has been looking at, from the theoretical side, how can the language model do such things, right? That seems to be very mysterious to us because you're not changing the parameter. The model was fixed, right? But then how come it can actually do all these different tasks? Some of the tasks was actually not trained on explicitly by the language model. So Stanford has this 2022 paper that they were using hidden Markov model to think about this inference process, but they didn't provide any specific algorithms to improve the existing in-context learning paradigms. There were people thinking that even though there's no specific gradient descent that is happening in inference time, but maybe the model is doing something similar, right, to the gradient descent learning. So that, I think, are some interpretations. Our particular theory is that we think during the inference time, the language model can be considered as a latent variable model in the sense that, if there's one formula you need to remember about language model, this is the formula, right? So this is basically in the training time, in the pre-training time, you're taking all these prior words, right, to predict the next word. Okay, so that's what the formula is telling you. Okay, you're predicting the next word. That's what auto-regressive language model are in the pre-training time. So what we are hypothesizing is that we could get some inspiration from topic models in the past by thinking that, okay, in the topic modeling, literature, there's the latent distribution of topics. You can draw it from some prior for specific topics. This latent representation, you have a multinomial word distributions associated with each topic, and then you can actually try to infer, right, your data. And what we are, thinking is that during the inference time for language model, you're always trying to generate, right, this language model probability of completing the query, right? So you have a query that is WI to T, right? That is your prompt. And then you want to continue, right, the generation. You want to generate the continuation. How should you generate, right, such probability? We believe you can think about the generation process from the, latent variable perspective, meaning that when you're typing the prompt, right, the model is trying to infer a latent representation of the task that you're trying to solve. Okay, because first of all, the language model has to figure out what task you're trying to solve. That is the theta, right? So you can think about it as a high-dimensional vector, and then based on the theta, it generates the continuation based on the inferred latent variable. Okay, that's basically the theory. All right. So how is this latent variable formulation going to affect us in context learning? Well, because you can formulate this as inference procedure, you can also turn this into in-context learning, right? By simply just replacing your prompt in here with the K-shot demonstration for the particular task that you need to select. And X here is the testing example. Okay, you have the example, you have the demonstration you need to select. What is my probability, right, of generating PY given this conditional distribution? And because we have this latent variable Bayesian perspective to it, I can decompose, right, this conditional probability into two parts. The first part is this left part that given the language model inferred, okay, you're trying to solve English to French. Okay, you're trying to solve, Korean to English translation. So based on this information, how do we predict the label, right, to generate a continuation? And then the second part is to automatically infer, right, such a latent variable. Given the prompt you've written, okay, looks like you're trying to solve, summarization. Looks like you're trying to solve question answering, right, or, other tasks. So that is the inference part. Okay, how do we parameterize, right, this particular, latent variable representation? Well, there are this data generation directions you can think about. We talk about multiple ways to think about the data generation process, but particularly for this example, we are going to assume that the data generation direction is basically the label or the continuation is conditioned on your prompt, right? And also your latent variable theta. So theta and x generates y. So that's the causal direction. But right, it is also possible to have another causal direction saying that, okay, it could be that x is generated by y, right? And theta. Again, that depends on the assumption, but both of them are plausible explanations how your data is generated. Okay, and like I said, theta, what exactly is the latent variable here, right? Theta is just a high dimensional vector, right? Think about as embedding, right, of the task or embedding of the topic. So theta is a high dimensional vector that is here, okay? And, assuming that, each particular task can generate specific value for theta, then we would, have a very nice scenario here that is conditional probability Py, conditional theta and x. This would give us the Bayesian optimal classifier to solve, right, particular solution if you can correctly infer, right, what task, right, you are trying to solve with the language model. So that's, the nice, thing we can get out of it from the Bayesian, optimal classifier theory. Okay, so that's the theoretical part, but then the question is, why are you doing this, right? Like, does that give us any insights or does that give us any benefit? Well, it turned out there is this practical benefit is because we can decompose in-context learning into two parts. The first part is what we call latent concept variable learning. Some of you may be familiar with, soft prompt tuning or parameter efficiency fine tuning that happened around 2021, 2022, that you can actually use soft prompt tuning, right, to learn the theta representation for the task you're trying to solve. And then the second part is related to demonstration selection. So once you have this classifier, can you automatically infer what is the optimal combination of the examples, right, I can use in-context learning such that it gives you the best performance. So that is also another component. That is the second component in this framework. And again, here, you can have the in-context learning formulation, and that, if you infer theta correctly, that this conditional probability will get closer to the Bayesian optimal classifier. Okay, so that's the theoretical part. The overall overview of our algorithm is actually quite simple. There are three parts. The first part, like I mentioned, is the picture on the left. Here we are learning each task, right? You're learning the theta. So how do you do it? Well, we do it in soft prompt tuning. And in soft prompt tuning, you have this vocabulary, right? You can deal with the language model. We create additional entries in the vocabulary, right? And all these, additional entries in the vocabulary, you put them together with the input such that when you optimize for your specific task with the cross-entropy loss, for example, text classification, you're optimizing the text classification accuracy, but at the meantime, you're learning the theta, which is the representation of the task, right? So you're doing classification, optimizing for accuracy, but meanwhile, you learn theta, right, for your specific problem. So we can do that for all sorts of different tasks, different data sets you might have. Once you have the soft prompt tuned classifier, and the second step becomes selecting, right, the best example. So what we can do is to send, right, this XY pairs, which is for example, French and English examples, or send all these different pairs to your learned classifier, and you pick, right, the ones that give you the highest posterior probability. So this would be your top examples. So once you have these top examples, what do? Well, the next step is very simple. You put that in GPT-3, right? So you put them as example in context learning and see if that gives you any performance. What is the benefit of doing this? Why are you doing this? Well, that's because for some of the bigger models, for example, GPT-3, GPT-4, you cannot fine tune it, right? You cannot afford, right, to have the resources to fine tune it, such that if you learn it from GPT-2, the smaller model, you can take these examples and put them, in the bigger models, right? And improve the performance. So empirically, that we showed comparing to a randomly selecting examples versus the similarity-based one, right? Select the most similar examples or using the retrieval or RAG-based approaches. Well, that gives you certain performance, but our solution using this latent variable algorithm give us the best performance. And the interesting things is that it generalizes across the family, right, of the GPT model. And we validate this in 8 text classification data sets, and each experiment, we run it 5 times. Again, interesting observation is that we can actually learn the tasks, the soft prompt tuned models from GPT-2 extra large, which is only 1.5 billion. We learn the examples, select the examples, and then send them to GPT-3, right? At the time, we cannot actually fine tune GPT-3. That still gives you better improvements, right, for your task. So this is, a very nice benefit of doing this particular solution. Okay, so what are some observations? I think, everybody's trying to figure out how LLM work, right? So we offer a interpretation that is a latent concept variable learning procedure for in-context learning. We show that, well, indeed, you can use this to interpret language model for in-context learning, but certainly such behavior of LLM, maybe they're still coming, right, from your pre-training data distribution. But in general, I feel like understanding language model could be a good way, right, to do research that does not require a lot of resources. Very recently, in addition to in-context learning that happens at inference time, we also started to understand pre-training, okay? So my student, Xingyi, so we started to, understand whether these language models having this reasoning ability by aggregating, different inference paths. So some of you heard about, chain of thought reasoning and other reasoning techniques. So we are hypothesizing that it could be that because there are, multiple paths, right, that leads to the reasoning results, maybe there's a way we can parameterize this, reasoning paths using exponential family. And because you can do it, meaning that, well, for the pre-training corpus, if I use this specific, random walk-based ordering of the pre-training examples, well, we show that you can actually give you better performance comparing to randomly organized training data. So that, I think is also interesting line of research, trying to understand the impact, right, of pre-training data with regarding to the reasoning capability. But this is just a particular theory based on random walk we have. Okay, so that is the, the first part that is about the science of language models, trying to understand, right, particular, behaviors of language model. If there's any questions, I can answer the question now, or we can hold on to the questions towards the end to have more discussions. Yes, please. Mhm. Mhm. Yes. Mhm. Yeah, so that, thanks for mentioning that. So we are aware of that paper. I think that paper is orthogonal to what we are talking about here. So they are explaining it from the perspective of evaluation metric. I think that's a very interesting angle, but we are talking about it mostly from the inference perspective. How can a language model solve, right, all these different tasks, even though you may not have seen this task before? So our particular interpretation is that, the language model may be inferring, right, a latent representation of the task conditioned on your prompt, and then it generate a computation. So we have this Bayesian view of this process that I think help us to understand, why these models can solve all these different tasks. Whereas I believe there's also, like you mentioned, that paper could be interesting directions to look at evaluation. So I think the nice thing about LLM is that there are all these different pipelines, right, that you can look into I think it's worth looking into all this direction, not just evaluation, not just in-context learning, but the previous slide also talk about pre-training. So I think we need more understanding of LLM from different parts, because my view of this process is can think about it from the computing perspective, right? Compute resources perspective. There's pre-training, there's a fine-tuning, there's the in-context learning, there's the inference. You can distribute compute, right, to different parts. Even in the evaluation, right, you can design how you distribute the computing. So all of them, I think, are quite interrelated. Mm. Sure. Mhm.
Concept reasoning, random walk relate to attention-based mechanisms as well as architectural.
Yeah. So that is, again, an excellent question. So in that paper, we also attempted, right, to look at this from the architecture perspective, and I believe it's also related because there's also this question from the transformer architecture perspective, how this model is doing the inference. Again, I think even if you look at the transformer architecture, the model has all these different layers, right? Does it all only follow one path to give you the result? Probably not, right? There could be actually multiple paths that is actually performing the inference. So I think in addition to the data perspective in terms of the multiple paths, while there could be also multiple paths in the architecture that leads towards the inference. But the challenge of doing those line of work is that it's very difficult to study architecture in the academia, because you have to scale it right to a certain point to really make the point. But this is a very very nice question that I think is not just the pre-training data, but there's also the multi-pass aggregation aspects in the architecture too. Mm-hmm.
Okay, another question. There's
Mhm.
been a paper arguing that, yeah, well, this is the same paper
Mhm.
that Sheikh mentioned,
Mhm.
Sammy's paper.
Mhm.
So, what are your thoughts? Could we just investigate LLM reasoning at small scale to understand large scale ones?
Okay, so that's, I think, what we are hoping to, because indeed, once GPT-4 came out, my student, they started to use GPT-4 a lot, right? And then last year, I think we spent how much, like $100,000 US probably on just calling the GPT-4 API. But then people were telling me that that's not science, because you're just calling the API. So I agree. I think it's not just using the small model to study the large language model, but also I think, we can do more things, right, with the smaller ones. Smaller ones, usually the white box models, you have access to the entire model weights, and you look at the log odds. There are a lot more things you can do. So I definitely agree. I think we do much more in the smaller models right now. But again, because we cannot scale that to the large model, so then there's also that validation part. There's a lot of people looking at like Mamba or this, state space machines. But again, I think we need to generalize that to bigger models too. Mhm. Okay, just for the sake of time, I think I need to continue because I still have two parts I have not finished. So we should continue. Okay, the second part is addressing the problem of solving more challenging, reasoning problems in language model, and also to achieve more faithful reasoning results with symbolic solvers. So the second part, I talk about neurosymbolic reasoning a little bit. So this is a work led by my postdoc Liang Ming and PhD student Along and Xingyi. This work was also published at the EMNLP last year. And the funny story about this work is that we released this paper on arXiv, and then OpenAI and Google DeepMind immediately contact us. They're telling us that they were actually working on very similar things. So it seems like, in the past, people believe you go from GPT-3 to GPT-4 with scaling, you would solve all of the hallucination issues. But turned out it was not the case, right? So I think there are a lot more people looking for alternative paradigms in dealing with hallucination in NLP. Okay, so we are sort of like half an hour into the talk, and it's a time to do some exercise in Alice's course. So I have a pop quiz and exercise for all of you to do. I have this specific question, and hopefully you can help me to solve. So there are 5 square blocks stacked on top of one another, right? 5 square blocks stacked on top of one another. So you're given the following information. You have 2 premises. One premise is the second from the top block is green. And the second premise is the fourth from the top block is not green, okay? And you need to assume that both of these 2 premises hold. Can you prove or disprove this following conclusion? The conclusion is there is a green block directly on top of a non-green block. Okay, maybe I give you 30 seconds to think about this problem, and you can tell me how to solve this problem. Okay, so right. So this is very funny because I think we sort of passed the peak age, right, to solve this kind of questions. Because if your high school math teachers are here, they're gonna tell you how to solve this problem, but just visualize it, right? You can actually draw this in, 2 situations. One situation is this situation that the third block is green, right? So that's the first situation. The second situation, if you visualize this, well, S3 is not green, right? So these are the 2 cases because the definition is about the second block and the fourth block. So there are only 2 cases for S3, right? These are the 2 cases. From these 2 cases, you realize, okay, after drawing this, after sketching this on a piece of paper, in both cases, there is a green block, right? Directly on top of a non-green block, right? Then you solve the problem. So what I'm trying to, tell you in here is that if you give such questions to GPT-4 using natural language only, GPT-4 does not solve the problem. The accuracy is really low. It always hallucinates and gives you random results for many of these problems. However, if you can represent, right, this particular problem into formalized formal logic or symbolic logic, right? For example, in formal language, you can actually call an external solver and solve this problem perfectly. Okay, and why is this important? Well, if you think about the more difficult problems, a lot of them, you need to make sure, right, these language models are following the rules, right? So for example, let's say you're planning the next trip to Busan, and what people are doing right now is that you're using all these different apps and trying to, look at your budget constraint, your time constraint, everything, and then you do it manually. But can language model, right, actually follow these rules, right, and correctly give you the outcome? This is not too easy. So we found that if you formulate this into a symbolic language and you call an external solver, that usually gives you much better result. So what this is telling us is that, nowadays everybody likes natural language and LLMs. You want to use LLM to do reasoning. It is very flexible. It solves all sorts of different problems, but it's not very reliable, right? For example, in this query, it doesn't solve it really well. And it has low variability. You do not know whether your result is correct or not, right? In terms of verifiability. And if you look at the AI in the old days with symbolic reasoning, nobody likes them anymore because they're not very flexible, right? Because you cannot easily adapt that, right, to your specific problem or language input. But they are highly reliable and they are verifiable. So is there any way we can actually combine, right, the best of the both worlds to improve the performance? I think it's possible, right? Because my whole PhD was actually on probabilistic logic programming, which was kind of a very interesting area that we used to think, okay, maybe we can have a world model, right, to represent the world. Here's the famous Markov logic network from 10 years ago that assume, right, you can actually ground individual items in your database and knowledge base into this Markov random field. but turned out that it is impossible, right, to solve the inference problem because the inference is intractable, right? It would take too long to give you the answer. So that doesn't work, unfortunately. But now I think there's opportunity to have a collaboration between language models and symbolic solvers to solve these different problems that I just showed you. For example, you can use in-context learning that I introduced in the first part and teach the model to translate the problem from natural language into this formal language, right? And then I can use external tools and I can use external solvers to solve it. And if I have, errors in the compilation, I can take the compilation errors and send it back to the language model and ask the language model to reformulate or retranslate, right, this particular problem into the formal representation. And hopefully that would give us better results. So, so that's why we think about, from the grounding perspective, you don't have to build a world model. You can start with your question. So that's your natural language question. You use in-context learning and teach language models to translate that into a machine symbolic language, and you execute that with an external solver. For example, constraint satisfaction solvers, so that give you an outcome, and then you incorporate that, right, in your final result. Or if there's an error, like I said, you take the compilation error message and then continue to refine, right, the translation process to give you better results. And we tried this with some multiple difficult data sets with different kind of reasoning. For example, there are deductive reasoning, forcible logic, constraint satisfaction. We look at all these different solvers we can use to solve these different data sets. The ARLSAT is the US law school entrance exam. That's usually the most difficult ones. I'll give you some concrete examples so you can see what kind of problems we're looking at. Okay. So solving this using language model to do the grounding and the structured learning is fairly easy. You write this, input, you give some examples, and then the output, right, would be the symbolic rules generated by the language model. And then we can, run it through the, external solvers. And there are two challenges. One is, certainly the translation aspects, right? So how do you translate that correctly into the formal language? It's not the super easy task. For example, what are the capability of the language model? What, training data or GitHub data the model has seen that affects, right, the translation accuracy for sure. There's also this connection to the AI agent research that a lot of people looking at tool augmented LLMs. But specifically here, we're looking at the reasoning perspective to solve more difficult problems that requires logical reasoning and constraint satisfaction. Okay, so how does that work, right? What does that look like in terms of comparing to some, standard approaches? So here we compare with two baselines. One is the standard prompting. The other one is chain of thought prompting. So you can see that with most of the data sets, especially the most difficult data set, ARLSAT, the standard prompting gives you 33% accuracy. The chain of thought gives you 35%. Using logic LM, our approach, we can achieve 43% accuracy on this data set, which was significantly higher than all of these baselines. Okay, and another thing you can visualize is the reliability, right? When the problem gets a lot more harder. So for example, here we can visualize the number of reasoning steps, right? Or the reasoning hops, and how is that affecting your accuracy? So you can see if you use purely language to do reasoning, when you get to 5 hops, the accuracy drop, right, significantly when you get to 5 hops. But with logic LM, even if you get to 5 hops, you can still stay above, right, 70% accuracy for these proof writer data set. So that's fairly interesting, meaning that while doing reasoning, if you use natural language, that might not be the best approach, but you use this precise, right, program that usually give you more precise answers. So even though the language is intuitive, but for reasoning, solving this, precise problems, possibly, the code or the program language is still better. Okay, so I promise you to give you some examples about the law school entrance exam. Again, these are very realistic problems, okay? So let's say, you have this task, right, that we need to organize a one-day workshop at KAIST, right, let's say to do language modeling. And then we have 3 speakers that Alice needs to, organize, and they talk about different topics. Right now, what people are doing, the conference organizers, they're doing it manually, right? Because there are all these different constraints you need to satisfy, right? What is the, day schedule look like? Because, for example, the second speaker, they cannot give 2 presentations in a row. There is this ordering of the topics that is really matters. You should give this topic first, the other topic later. There are all these different constraints. That's why right now, when we're doing the conference scheduling, we're still doing it manually, right? But imagine if language models can do planning and can solve this complex constraint satisfaction problems, can teach language models to follow the rules, well, it's possible, right? In the future, we can do this with the help, right, of the language models as well. So right now, again, accuracy is still really low, about 30 to 40%. Okay, so that's that. But another thing we found is that how you formulate this also matters, right? If you formulate that with the wrong reasoning tools or wrong language, that still won't give you the best results, right? So formulation also really matters. So 2 things I think could be interesting. One is to decide what is the reasoning tool, reasoning systems that your AI system should use. The second thing is, of course, how do you correctly, right, translate the natural language input into, code or, formal representation. So both of them, I think, remain challenging. Okay, before I move into the third part, any questions at this point? Yes. Mhm. Mm. Yeah. Excellent question. So when there's a translation error, what we have is that these external solvers, they will give you error message. So what we do is that we take the error message and we send it back to the language model and use that as feedback and teach language models to reformulate the translation. And in some cases, it can give you about 2 or 3% improvements after you do this, what we call self-refine, as feedback signal for the language model to refine the translation.
Self-refinement, what kind of error message do you get? Syntax errors in the translation, or do you also check some kind of semantic errors? Maybe you might say your translation formula could be 10 variables or something like this.
Yes.
That might generate some feedback to you.
Yes, yes.
Something will be on the syntax error.
Yes, so we have this paper at the MNLP. It's called MAF. MAF is a multi-aspect feedback that we specifically look at not just syntax errors, but also there are other, potential feedback channels and feedback we can use to improve the feedback process. You're exactly right. What we notice in the error in logic LM is that sometimes there's no syntax error. It compiles, but the answer was wrong because it could give you a valid rule and you run it, but it's just the semantics were wrong. So you're definitely correct that we've been looking at both the syntactic and semantic feedback, but that was a different paper. Yeah.
If the problem formulation, there are several. Okay. Do you have any insights why LLMs work better in symbolic format than in natural language?
Yes, so that was what I just briefly, explained. I think natural language is very intuitive, right? It's very flexible. But you think about why do you use math in your papers? Well, that's because math is very precise, right? I can, write different 10 paragraphs to discuss logistic regression, but people who are reading it will just have 10 different interpretation. But if I just write out, the formula for logistic regression, nobody would disagree, right? That is, how logistic regression work. So that's why I think in some cases, and there's actually, a lot of paper along this line, using code or using this formal representation usually give you better results and more precise result for the task that require this precision, right? If you're talking about, creative writing, you don't care because there's a 200 ways how you can write a great thesis, right? So creative writing doesn't matter. But for some of these tasks, you have to give a very precise outcome using natural language itself as the medium. You see in that previous multi-hop example, the accuracy just keep decreasing when you increasing the number of hops. So I think looking at program or code as a precise medium, to do reasoning is very critical to solve some of this related tasks.
Yeah, the next two questions are maybe related. If the problem formulation matters, how can we evaluate the formulation quality? And then a similar question here, the difficult part here is to make a complete logical solver for each problem containing all the domain-specific language correctly.
Yeah. So there are two ways we can do the evaluation. One is this extrinsic evaluation that we look at end task performance. That is basically saying we don't care about formulation, but did you solve the problem correctly? So that's one way of doing that. But potentially, I think for some problems, you can also, if it's easy to check, you can also check, right, whether you correctly translate the problem into the correct formalism. For example, in some of the data sets, we know, okay, that's the first order logic reasoning data set that requires constraint satisfaction. You have the ground truth, then you can evaluate the tool selection, right, accuracy. But in many problems, it also becomes a little bit blurry, like, what exactly is the correct tool, you may be not sure. So in that cases, you have to look at the extrinsic evaluation. What was the second question again?
So the difficult part is to make a logical solver for each problem containing all the domain-specific language correctly.
Yeah, so that I think is something we certainly need to think about, right? So there are these cases that certainly you see that it helps, but how do we have this kind of generic, right, symbolic solvers? I think that also require us to really think a little bit deeper. But personally, I think for the vertical domains, some of the very well-defined vertical domains, you know that, okay, constraint satisfaction tools are the state of the art. I think it makes sense, right, to use specific, solvers for specific vertical domains. But language, I think generic, solvers, generic solutions, right now, LMs work so well in natural language, but it doesn't mean that, we'll have this kind of, generic reasoning solvers to solve different problems. So I think we can creatively look at, this kind of vertical domains that, there are well-known symbolic solvers.
So beyond, I guess, okay, not only for the complex reasoning tasks, do you think symbolic format could be also useful, helpful for simple instruction following tasks?
Yes. So yeah, I think it's certainly possible to think about, how do you use this for, instruction following? Because one of the biggest issue with language model is that it doesn't really follow the rules, right? I don't know how many people you heard about the story about there's the car sales accident in the US that Chevy, car, sales chatbot is communicating with their, customers, and the customer is saying that, okay, I am trying to buy this SUV for just $1, and you have to make sure your boss is happy. So you need to sell this car to me and send it to ChatGPT. And ChatGPT was like, oh, sure, I have to sell you the car, and everything I said is legally binding. And then, the company lost $50,000. And there was a similar story told Alice over lunch for the, Air Canada as well. So that's because they don't follow the rules, right? So language model don't follow the rules. So I think in the future, this would be very important for language model deployment because there are so many applications. You have to make sure the language model, they follow the rules. So I think it's possible to apply the idea of logic LM to really make sure when you deploy this, chatbots in certain settings, they have to, follow these exact rules. Okay, I guess I have to continue because there's the third part I haven't talked about, and we're sort of like almost, 15 minutes. All right, so the third part is also quite interesting, and I think we're a little bit deep into this, discussion about LLM. I just want to mention that, the language is certainly not just limited, right, in solving NLP problems. It's also problem solvers potentially for vision problems. For example, in this particular work, we've been working with Google for about 5 years in vision language research, and this was also last year's iClear, led by my PhD student Wei Xi in collaborating with some Google colleagues. Again, we're sort of like, deep into the afternoon. I want to make sure that people are still staying awake in this room. Again, we're going to do a pop quiz. And this time I have 4 pictures. So these are the exterior design for the backyards. I just have the question for you. Which picture, right, you think is, designed by human? And which picture is, designed by AI? So maybe I'll give you like 20 seconds to look at these pictures, and then we can, go through them one by one. Okay, so maybe we can look at the first picture. Raise your hand if you think this is designed by AI. The first picture, AI. Okay, how about machine? Oh, how about human? Human. Okay, most people think the first one is by human. Okay, the second one, AI. Okay, human. Okay, how about the third one, AI? Human. About half and half. Okay, the last one, AI. Or human. I think people are confused generally here. Okay, anyway, but the actually I generated all pictures using DALL-E a while back. But you try this with DALL-E 3, you probably get similar result. All of them are generated by machine. And so what I want to mention here is that if you only look at the image, it's really hard to tell, right? But if I give you the prompt, sometimes it becomes easier. So here, because when you actually design things, right, again, you have a lot of constraints if you really want to design, right? So in this case, I have this constraint. I want to do a cozy backyard with a fire pit on a patio, and I want to have a raised bed garden, vegetable garden, so I can, grow vegetable. I want to have an artificial turf, right? So the kids and pets can play. They want to have some fruit tree, right? And I say this is Southern California. So once you have this user input, you will realize, sometimes things are not correct. So for example, the third one, right, it's really funny that you actually have the fire pit on top of a vegetable garden. That would be horrible, right? That you'll be burning your vegetable, right? You grow in the vegetable garden. So that is an error you can tell right now. The first one, the grass doesn't look like it's artificial. The second one, there's no patio, right? There's no place you can stand, basically. And the last one, there's no grass, right? So what we found in this kind of AI generated image, whether it's DALL-E 2 or DALL-E 3 or Stable Diffusion, in some examples, they, worked out so well. But if you carefully try, right, with the actual use cases, you realize there are a lot of these compositional errors and attribute binding errors and missing objects. So here's an example. You want to have a brown bench in front of the old white building, but building is not really white, and then the bench is also not quite brown. The second one is probably more obvious, right? Specifically, you say you want to have a red car and a white sheep, but then you realize the sheep is not white, right? The sheep is red. So there's some color leakage, right? That attribute leaked into that sheep. The third one is more common, right? It's similar from the previous example. So I said that a blue backpack with a brown elephant, but there's no elephant, right? The elephant is missing. So that is also very common. So why is this diffusion models giving us such errors? Well, we really want to solve this because actually when you're trying to use this for your practical applications, this would matter a lot. But we also don't have the computing resources of training, right, another stable diffusion from scratch. So that would require a lot of A100 GPUs. So what we're thinking is that maybe we can, have a training-free approach, right? That we can fix these errors with Stable Diffusion by correctly, solving the problem without, right, retraining the model from scratch. So that's sort of the rationale of how we are doing, trying to do this kind of things. Just a little bit of background. Stable Diffusion has been out for quite a, few years right now. I think Stable Diffusion 3 is sort of the state-of-the-art, right, diffusion-based model that does this text-to-image synthesis. It synthesizes the output from noisy pattern guided by some text encoders, for example, clip text encoder, based on this cross-attention conditional mechanism. So the whole architecture looks like this. You have some noisy pattern, you have some clip-based text guidance, and then you have the diffusion UNet, and gradually, iteratively, right, you're denoising from the noise to the actual output that you're generating. So what we notice is that maybe we can leverage some linguistic knowledge, right? For example, parse tree to improve the knowledge binding process in Stable Diffusion. So potentially, if we can figure out, right, this linguistic units, and we can put these linguistic units and use them to strengthen, right, the semantic encoding in the in the Stable Diffusion process. So hopefully we can get better results this way. That's what we call structured diffusion guidance, and trying to leverage linguistic structures to improve text-to-image decoding. And the solution, like I said, is quite simple. You don't have to do pre-training. You don't have to do fine-tuning. You can use this simple solution by parsing your prompt and extract, right, this semantic representation for these phrases and put them back, right, into the embedding space for Stable Diffusion, such that you have the original embedding, but you're going to sort of regularize or strengthen, right, the representation by pulling the minimal non-phrases, right, and put these embeddings back in these attention mechanism. So hopefully you can strengthen the semantics and improve the performance. And finally, you can compute just multiple values from this new embedding space and use weighted average to generate the output. So there's no pre-training, there's no fine-tuning, only fixing it, right, in the embedding space in the inference time. Okay, so what does that look like? Well, you first have to find the evaluation benchmark. So we create this benchmark, so ABC6K, specifically having multiple objects with these actions with attribute binding, have the CC500 corpus that has multiple objects with attributes to, test, right, the performance of this text-to-image generation systems. And we can also do human comparison and give a human judge, right, with our system results and also the other system results. And in comparison, people prefer, right, the generated results from structured diffusion comparing to Stable Diffusion and composable diffusion, which was a state-of-the-art baseline. But of course, this work was from a year ago. In the last year, there has been 100 papers trying to, look into research along this line. So they push the state-of-the-art much further. There are people from the graphics community who got interested in this line of work. Of course, there are people, in NLP who also got into this line of work to improve generative AI. Okay, but again, a nice thing about this evaluation is that it's crystal clear, right? For example, the second prompt, you look at, for example, a red bird and a green apple, you can see clearly, right? The Stable Diffusion generated bird is not really red, right? So it's like reddish or greenish. And then composable diffusion, there's no bird. In our result, there's really a red bird, right? And a green apple. So you can actually see, right, whether your output is correct or not. So this is kind of nice way to do this kind of evaluation. Here are some observation that I think, this kind of compositional problems still exist, even in DALL-E 3 and some of the latest systems, we still realize this issue. So how do you teach, right, AI models to have these compositional skills? This remains a challenging problem in generative AI. And for language vision, I believe the two communities are getting closer and closer, can use linguistic knowledge to solve a lot of the difficult, visual vision problems, perception problems. And there's also this interesting perspective of not, really training this model from scratch, but how do you fix, right, this kind of, compositional problems in generative AI systems. Okay, some of the latest work following, this text-to-image compositional idea, including our latest work with Google from New York last year on leveraging the idea from logic LM to improve, right, text-to-image generation. So many of you have your own website. You know that when we're building our website in the design, we have CSS, right? We add a markup language to do the layout. So I have this idea that maybe we can have, right, CSS as an intermediate language for text-to-image generation, such that you first translate the prompt using language model into a CSS layout, and then we can forget about Stable Diffusion. We can use layout to image generation tools to directly skip, right, diffusion models to generate, the figure. And turned out that doing this gives you much better results comparing to the prior work. And that also applies to 2D and 3D planning for indoor planning as well. So again, like I said, using some sort of, formal representation for many of these tasks requires, just a little bit of additional computation. This is also in context learning, but it does give you, high quality results so that you don't have, for example, nightstand on a bed or some of this, simple errors. Okay, so we still have a little bit of time left. I want to talk about limitations, challenges, and conclusions. So what are some limitations that we haven't really quite talked about? I think the science of LM part, right, is kind of very important to really understand the reasoning ability and also the performance in various vertical domains. Misinformation, factuality, hallucination remains challenging because you can see even for people, right, it's very difficult to tell. This generated image or generated video. So how do we deal with the impact, right, of this LM generated contents or AI generated contents? So we have a few papers along this line. We have a new paper at iClear next month, actually this month in April, on detecting LM generated content. It's called DNA GPT. You can look into that, but there's also, the generation aspects for multimodality as well. And also, how do we deal with bias, right? Fairness, privacy, and copyright issues. I think all of these are interesting research directions, looking at vulnerabilities, the safety of the language models. There are a lot of the technical areas that we can work on in academia, including watermarking, jailbreaking, machine learning, that these are very active interdisciplinary areas in AI and ethics and responsible, technology. Okay. So specifically for responsible AI, we, had this center at UCSB. I started in 2019. Right now, we grew it into 60 faculty members from 20 departments, and we have all these different annual events to facilitate the discussion and collaboration between faculty and students to have more joint projects. In my group, we have a lot of students looking at disinformation, fact-checking, started, way back, and now we're looking at AI-generated contents. We've been looking at fairness and attribution issues, looking at, gender bias, gender seniority bias, looking at, dialects, looking at memorization, generalization issues. Recently, AI safety issues regarding to minors and children using AI, and also looking at, some of the vulnerability of the open source and the black box LLMs. Okay, to sort of conclude today's presentation, I think we need the principled algorithmic designs and the analysis for understanding, all these different behaviors of language models. We need to build collaborative AI systems to really think about, modular AI design and solve these difficult compositional issues that AI systems cannot solve right now. And of course, we need to have an interdisciplinary team, right? A holistic view and solve this responsibly with this different and difficult AI problems. And a few weeks ago, I think one of Alice's tweet went viral on Twitter, where she calls for collaboration. And I think a lot of us, we feel the same, right? Because there are just so many papers, data sets, benchmarks. It's very difficult to follow for both students and faculty. I agree. I think that's why I'm here. That certainly I can give you some examples of collaboration. We have a lot of academic collaborations, but I think it's also industry and academic collaboration, right? We need to seek new paradigm. So my student Ray is graduating this year, and he started this, vision language-based visual editing work 5 years ago. We had a first paper at EMNLP 2020. At that time, it didn't work really well, but recently he helped Apple to build a pretty impressive image editing tool on iPhone, and a lot of the major US media is calling this as a revolutionary AI-based model. I can give you a demo. So this is on his iPhone. He can say, okay, take a picture of the countertop, and he can, type, okay, add a pizza on the table. And after a few seconds, you should generate pizza. You can do it with other things. You can change the background. You can, do other editing of your occasion pictures and do other things. This is very interesting. It could be that Apple will be pushing this to 2 billion iPhones, right? You can see this is actual research our students are doing. Is impacting everybody on the society. I think they're still working on a few things to make this really reliable. But in the future, I think this potentially certainly could, be deployed into mobile devices. Another example is that, in the academic collaboration, sometimes it's not just the collaboration within the computer science. So we had this collaboration with neuroscientists started like 2 or 3 years ago that we, had an excellent team of experts at our university who is good at doing this, state-of-the-art 2-photon imaging of the mice, right, data. So I'm not a mice person, but there were this mice, person at our university who can measure the precise activation of a single cell, right, in the mice. And then you can actually work with the mice to do, all these navigation problems or, VR games. And then you can measure their brain activity. And then you can take this brain activity, right, and then train a GPT model and use this model to predict, right, this behavior of this mouse. For example, you can look at the local motion, direction, eye tracking, velocity, all these different things you can predict. And we show that with neuroformer that you can predict it really well. So this is mostly led by my work, my PhD student, Antonis Antoniadis, and this will be presented later this month in Vienna in iClear. But this is just another example of collaboration that we could have to work on in the academia. Okay, so that summarizes sort of everything I want to talk about today. If we still have time, happy to take additional questions. And thanks all for coming to today's talk. Yes.
Yeah, thanks for the great talk. Your second project and the last project that you shared emphasizes sort of the importance of good intermediate representation type of problem. And I think to formulate the problem, I think you need to look at both sides, whether LLM is capable of generating that representation and also looking at the domain itself and seeing if that representation makes sense for that domain. And I'm wondering, to generalize that kind of approach, do you have any insights into how you make those decisions about what representation to use, or are there any recipes that you came up with as you're approaching these problems?
Yes. So I think the key recipe is language and X. So language and something. So let's take computer vision, for example. I think computer vision faculty and students can disagree with me, but I'm gonna say what I'm going to say anyway. So for ImageNet, right, that was really the revolution for these kind of, deep learning era about, more than 10 years ago. At that time, human were labeling the ImageNet data, right? So you were generating a text label for individual images. You can do that with a million image that costs a lot of money, but that does not scale very well. So I think another breakthrough in computer vision was 2020 or 2021 with OpenAI's CLIP model. So they found out that you don't have to do the annotation. You basically takes the image and their caption. So this text can automatically supervise the learning of the visual concept. Because imagine if you're learning, the environment pixel by pixel, this would be just too slow, right? Then, okay, finally, with a few million example, you learn that that's the door. That's just very inefficient. But with language co-located with text, so that's much faster that you can associate concepts, right, with the perception. So that's why I think after CLIP, computer vision really took off, that there are people using CLIP for medical domain. There's a BioClip at CVPR this year that was selected as oral presentation. There was this, CLIP for robotics research. You can also apply CLIP for robotics research. People show you guys state-of-the-art in object detection with CLIP and so many different things. So I think we can do that for other area too, but you need this kind of text and something, because text, I think, is a very nice way to organize the human concept and human knowledge. And that's, how humans are communicating with each other. So that's why you see all these different domains. For example, time series prediction. People realize if you have text and time series, you can do similar things, right? Like computer vision and NLP, that you can actually use that to learn, right? The time series and what does that mean to interpret this continuous signals as well. And of course, people show that you can do that with videos, right? And there are Sora and other stuff that is happening. So I think the key recipe is language and something, because language is, in some cases freely available, or you can annotate the language data that allows you to learn the association of different signals together with the concept. Yeah, go ahead.
Talk about the inductive bias. And I'm curious about what you think about inductive bias and whether you explore, for example, putting the original together with the intermediate formatted version.
Right. I think inductive bias is very important, and there are a lot of designs. I think in machine learning are still based on the inductive bias introduced by human. Transformer was a very good example, right? I don't know how many people remember, but there was this neural architectural research that happened for about 10 years and didn't go anywhere. People realized, well, I can still use transformer to beat all of this NAS, right, based approaches. So I think, there are still a lot of human design that are the CFD-art very important. In this particular case, I think looking at language jointly with code to do reasoning, it was very useful, right? So last year, there were 2 papers basically showed this give you state-of-the-art in mathematical reasoning, financial reasoning. One paper is from CMU, it's called PAL, P-A-L. The other paper was from Wang, my former PhD student from Waterloo. He had this paper of program of thought, right, that combines program reasoning together with text. So I think certainly combining these different signals and use multiple channels to do reasoning, certainly this has more information, because if you're only using text as the communication channel between different modules, sometimes it's not enough and there are limitations.
There's a question in the chat says, as someone who's out of the AI field, is in software engineering, but uses AI as a tool to do research, what can I do to collaborate with the greater AI community?
Yeah, so I'm happy to say that I think AI, and software engineering, this would be huge, right? Because I've been talking to many of these companies. Some of the company, they spend just billions of dollars for software engineering development every single year. So there is this, opportunity to use AI to revolutionize software engineering too, because if that can improve the efficiency of the programmers, if they can, certainly cut down the cost of software development, maybe we'll not just have more efficient, but potentially could be more reliable, software too, because not everybody are, good at coding. My advisor wouldn't code better than me. So in many cases, you can see, for example, the Boeing example that, there could be the cases that, this coding errors leads to some really, not so good outcomes. But potentially there's a way that maybe we can do better program synthesis with the help of AI, so that, human AI collaboration, we write better code. At least this is what my PhD student was telling me. Everybody was using Copilot and they're much more efficient. So if you haven't used Copilot, of course, you should use it to help you. But yeah, I think long story short is I think program synthesis or software engineering AI, this is a very exciting area. I would say this will have a lot of the exciting things happening across all this different industry. Mhm. Mhm.
Back to language plus stuff.
Mhm.
So like using code, I think it works really well for like questions that have like that needs like precise answers. But like most of the language related stuff are like they don't have like certain. So for those kind of questions, for those like problems, like something that has very subtle meaning, what would be the language? Like, what would be the
Right, right. So, some of my students, they're thinking about, how do we model the uncertainty, right? So there could be this probabilistic interpretation of the outcome rather than text only. So I think it's certainly possible to explore how to integrating probability into the language model. Right now, I think, there are people who's doing calibration work. There are people looking at uncertainty. I think it's easier to do that with the smaller models and white box models. The bigger models, it's slightly difficult to work with them. But I agree. I think, there are, sometimes it's not just text only or, black and white, but it could be, the soft cases that you may need, some sort of probabilistic interpretation of your data and probabilistic interpretation of the rules that give you a better outcome. But I think people are still trying to figure out, right, how to build, right, this kind of probabilistic neurosymbolic systems for LLM. All of these, I think, are open research problems. Mhm. Mhm.
If there are no more questions, I want to ask you one more thing and to close the talk. I think most of the audience, including the ones on Zoom, are graduate students doing active research in LLMs and machine learning in general, and they're probably all wanting to ask you, like, what are some specific research questions and directions that you think are particularly important for academic, especially PhD students, to pursue this year and next year?
Yes, yes.
Sort of advice for
Mhm.
NLP and AI research, PhD students, and then we'll close the talk.
Yeah, so I think I just want to build on top of what Alice mentioned. I think it is really important to think about, high impact work, right? And to really think about collaborative work, because do we really need like 10,000 papers in AI each year? Probably not, but there are really 10,000 accepted papers. If you combine all these conferences, it's really 10,000 papers. So that's why I believe now is a good time to do bigger projects with more people, but each of you will do fewer work, right? You will do small portion, but then together we're gonna solve a more difficult problem. So there was this one example that my senior PhD student along Albalac, so he's working with MIT, Stanford, UW, all these different institutions. They spent half a year, wrote this survey paper to understand data selection in language model. I think it's quite important because nobody knows, how these data were selected for pre-training for language models. But if you only write this paper yourself, you only have your perspective. So he was quite good. He invited all these people from all these different institutions. Everybody was helping him to write one chapter. And then together they have a really nice paper that covers not just pre-training, but fine-tuning, RHF data selection, instruction following, in-context learning. So that, was quite nice. I invite you to look at the paper. But I think my main message is that we need to avoid doing incremental work individually. We need to collaborate and, solve more difficult problems. And that would help you, right? Because if you yourself spend half a year doing, in the middle, you got scooped by other group. But then if you and another person finish this collaboratively in 3 months, well, that also mitigate the risk of getting scooped. Anyway, but I agree wholeheartedly with Alice that I think looking at more important problems and collaboratively solving them would be the future and will be very important for your graduate study. Thank you.
Thank you for second.
Great talk.
Thank you. Thank you.
I hope to,
Yes,
see you
yes,
again.
yes, yes.
I
Yeah,
can
thank you.
imagine.
Okay, absolutely. Yeah, thank you.
Yeah,
Thank
we'll
you.
keep you posted on how.
Okay,
things
okay,
go,
so
and
absolutely.
definitely need your
Yes,
input.
yes, 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 yes.
Yeah, enjoy your time.
Okay, thank you. Thank you, Junho, for joining us. Very nice meeting you. Oh, thank you.
I'm
Nice to meet you.
I won't kind of
Oh, great, great. I'm glad that somebody understand that. I thought nobody understand in the audience.
Oh, yeah. I think we like.
Yes, yes, yes.
There's something.
Yes, 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 yes. Okay, thank you, thank you, thank you. Yeah, I appreciate it. No, thank you.
So much.
Yes, yes, yes. I was looking at the schedule. I was like, oh, I have